Okay, so yeah, change of topic. I'll talk about Dirac fast scramblers, which are the extensions of the SYK model to higher dimensions. I'll talk about, and this work was done. The heavy lifting here was done by Jaewon Kim and Xiangyu Cao. So you all, I think, most of you know them. They've given talks here in this forum before. Maybe even on the papers, earlier related papers that I quote here, but the main paper I'll talk about is a pretty recent one from two or 3 months ago. So yeah, let me start and not give such a big introduction because I don't have such a long time. So first of all, just briefly, why is the SYK model so popular? Why are people interested in it? I think most of you understand. One reason is the connection. So first of all, what is the SYK model? It's a toy model with fermions interacting all-to-all with quartic or higher than quartic interactions. Generally, you can call it SYKQ, where Q is the number of interacting fermions. The one interest in this model comes from the fact that it's connected to black holes. The low energy theory is a Schwarzian theory that is thought to be dual to a black hole in ADS2. It also saturates the quantum bound on the Lyapunov exponent, and it can be calculated exactly in low temperatures. So it's a convenient starting point for starting to investigate quantum information paradoxes using the field theory side, using a microscopic model. And to those of you who are not familiar with quantum scrambling, the basic quantity that you want to look at in scrambling is how the commutator squared or out of time order correlation behaves in time. And an exponential growth is thought to indicate chaos. And one reason for that could be understood as an analogy with classical chaos, where in the semi-classical limit, this commutator squared basically maps to the sensitivity to the initial conditions. But there are other ways to see it. Not so crucial here. Another interesting reason to study SYK model, maybe more from the condensed matter side, is that it's model for matter without quasi-particles. It describes Planckian relaxation of in strange metals where the rate of relaxation is just proportional to temperature without any coefficient, or only h bar being the giving you units. So it could be a good starting point to investigate quantum phases and quantum critical points that show this behavior, and we don't have a good understanding of those in real materials, and which are actually not in a all-to-all interacting model. Which brings me to the question: what we would like to know, that this SYK model is a toy model. It's a toy model in 0+1 dimensions, and we would really like to look at extensions to higher dimensions, which will describe maybe gravity in higher dimensions, and from the condensed matter side, it will describe quantum critical points or strongly coupled phases that we don't understand, like cuprates that I show here. Linear resistivity in the cuprates is something that is related to this kind of Planckian relaxation, or at least thought to be related to this Planckian relaxation. There are other examples where there are critical points between heavy Fermi liquid phases and other phases in so-called heavy fermion materials. So there is a wide class of materials we want to understand, and maybe extensions of SYK models will help. And indeed, very quickly after this model was revived by Kitaev, there were attempts to generalize it to higher dimensions. So, for example, Xiaoliang and collaborators, as well as Leon Balance and UCSB, generalized it to higher dimensions by looking at a chain or a lattice of SYK models, where these sites are coupled by some quartic interaction. In this case, the exact solvability of the model is still due to in the large n limit, where you have an infinite number of, or large number of fermions on each site, is still intact. You can solve it exactly. The problem is that what you get is a Green's function that is totally local. So in this sense, in the sense of at least a single particle Green's function, this is local quantum criticality with dynamical exponent infinity. So you're really, in that respect, exactly the same as the original SYK model. Everything is kind of totally local, except, I have to make a reservation that if you look at 2-point functions like scrambling, and maybe I even make this point here. No, I should have made it. If you look at scrambling or transport, scrambling and transport do have non-trivial behavior along the chain, but it's sort of incoherent. The transport is incoherent and is diffusive transport, while there is ballistic scrambling. But it's not it's not a non-local quantum critical point. It doesn't have a dynamic, a finite dynamical exponent in the usual sense. So one can say, okay, maybe instead of quartic coupling, I'll just include quadratic coupling between these SYK dots. The problem with that is that quadratic couplings are immediately relevant and take over, and what you get is just a simple Fermi liquid. So you don't get any non-trivial fixed point, no fast scrambling or anything like that. So you get something we already know very well. So there were other attempts to generalize to higher dimensions. I won't go into them deeply. One of them was very fine-tuned model with supersymmetry. It turns out that it's a very special case of what I'll show here, but it's actually not trivial to see it. It's in this paper by Morgan, Stanford, and Witten. And then there is another model introduced by Micha Berkuz at Weitzman and collaborators. But that model had required very non-local coupling, so you can't really put it on a lattice or write it as a well-defined microscopic model. So in this talk, what I want to do is really introduce a very simple Lorentz invariant model with local couplings, can be put on a lattice that has non-Fermi liquid fixed point in both 1+1 dimensions and 2+1 dimensions. And we can demonstrate that it is fast scrambler, at least in some sense, in 1+1 dimension. Fast scrambler meaning maximal scrambling lambda equals 2 pi times t. Okay, so, and the outline of what I'll do is I'll tell you what the proposed model is, what is the field theory, and what would be kind of intuitive microscopic realizations of this field theory. I'll discuss the critical solutions in 0+1, 1+1, and 2+1 dimensions kind of together, and then argue that what is the nature of scrambling in this model in 1+1 dimensions. And finally, I'll comment on how our theory, which is in some sense a kind of modified large n theory, or modified large n limit to a well-known model, the Gros-Nouveau Yukawa model, how it relates to standard large n limit for this model. So basically that brings me to the proposed model, which is just a modification of large n Gros-Nouveau Yukawa model, or field theory. So you have Dirac, let me use, I'm supposed to be able to, sorry, I'm not sure what happened here. Slideshow. I thought there is a way to, oh, okay, yeah. You see my pointer? Yeah. So this, good. Yeah, so this is, oh, there is, it's not a very good, I'm trying this for the first time and it doesn't work so well. Sorry. Yeah. Okay, so here is, these are Dirac fermions, of course. And probably most of you know the Gross-Nouveau-Yukawa model. It's basically a model to describe mass generation or spontaneous symmetry breaking in presence of Dirac fermions. So the Dirac fermions are coupled to an order parameter field. When the order parameter phi, the bosonic order parameter, gains expectation value, then it generates a mass for the Dirac fermions. And in general, these bosons are have mass, and it's their mass or their coupling G can be tuned. What is different about our model compared to usual GN Gross-Nouveau model is that we're looking at a very special large N limit. So usually the large N limit means N fermion flavors, but there is one bosonic flavor or few bosonic flavors, depending on the symmetry. Here we look at the large N limit where both the number of bosons and the number of fermions goes to infinity, but the ratio between the number of bosons and number of fermions remains constant, and we call it gamma. And I'll call gamma for the rank of the model. It has to do with something I'll discuss in a bit, why I call it rank. So this is basically the model. It's well defined. Oh, I forgot to say that there is random translationally invariant couplings. So down here I show them. It's hard to point. Okay, so these are the couplings. They have a variance G squared, which I'll usually take to be positive, but in principle one can write down microscopic models where this actually will become effectively negative. But for now, I'll think of that as a positive number. Right, the number of couplings, you see each G like this is a rank 3 tensor. Okay, now microscopic realization. So first, 0 dimensions. This model in 0 dimensions is actually pretty well known already. In 0 dimensions, it's also called low rank SYK model if you want. And that's why I discussed rank. So here it is, the microscopic model. You can see it in the left here. It's basically a random model, but instead of the random coupling being a full rank matrix, it's a rank M matrix. So instead of Gijk, here I basically diagonalize this rank M matrix and rotate in terms of its Schmidt eigenvectors. But you can now write it as a Lagrangian, do a Hubbard-Stratunovich decoupling, and it becomes this model of fermions coupled to M bosons. So the rank is the number of bosons, really. So we basically say the normalized rank is the number of bosons over the number of fermions. So this is this model. It has maximal scrambling, we know that. It has an example in a particular point where gamma equals 2, it turns out to be a supersymmetric SYK model. And its fermion scaling dimension, unlike the SYK model where it's fixed, although you have only 4 fermions, you can tune you can tune the scaling dimension using gamma. So now let's look at 1 dimension. The microscopic realization in 1 dimension would be like just 1-dimensional lattice fermions that have the dispersion seen here. Now if I go to the long wavelength limit, I construct the fermion operator with slowly varying right moving mode and left moving mode, and I can write the Hamiltonian sort of like I would do for a Latinger liquid theory, I can write the Hamiltonian in terms of a field theory of left-moving and right-moving modes, and I'll have this low-rank interaction between them, sort of like in the low-rank interaction you saw in the zero-dimensional case, when I Hubbard-Stratonovich, and this interaction you see is a backscattering type of interaction. It interacts, it's an interaction between the density at 2kF with another density at 2kF. And once I do a Hubbard-Stratonovich decoupling of this interaction, I get exactly this coupling to a bosonic order parameter field. Now I do my large N limit where I have N of these fermions and M bosons. And again, the Dirac spinor is now the left-right components, and one can write the gamma, use the gamma matrices. Gamma 0 is sigma x in this case, and gamma 0 times gamma 1 is I sigma z. And the order parameter field is just a 2kF density wave order parameter. That's the bosonic field. So that's the microscopic realization, one possible microscopic realization in 1D. Of course, microscopic realization, and then we go to some kind of large N limit. What would be microscopic realization of a true large N limit is not so clear. Microscopic realization in 2 dimension is easy to construct on a graphene type lattice, honeycomb lattice. Again, if I look at a cape, I write a tight binding model, find the dispersion of graphene. I have a Dirac points at K and K prime seen here. Then my effective Hamiltonian close to the Dirac point is a Dirac Hamiltonian times some interaction of these slow modes near the Dirac point. And if the interactions actually favor a breaking of the sublattice symmetry and opening a mass gap in this way, then this will be the kind of interaction we have. Hubbard-Stratonovich decoupling of this interaction will give you exactly the same, Gross-Nouveau-Yukawa model with now the matrices, the gamma matrices defined in this way. In this case, one can of course consider other types of symmetry breaking, and for example, one can generate a quantum Hall state and so on. So one can look at different a large N model for different kind of symmetry breaking transitions here. So this is a microscopic realization. Now, how do we solve it? So due to this large N limit, fortunately, we can settle everything with sums of bubble diagrams, just like in the SYK model. It's a little bit more complicated because we have two species. We have a fermion and a boson. So the fermion is the line here, and the boson is the wavy line, and the fully dressed Green's function is this with the dot here. And one can write the Dyson equation for the fermions, and you see it involves a boson because a fermion can, because of the Yukawa coupling between the boson and the fermion, right? So you have that part, but you can, and now you can close the equations completely by also writing the Schwinger-Dyson equation for the boson propagator, which involves a fermion bubble. So this is the fermion bubble. This is, if you want, the boson self-energy, and this is the fermion self-energy here. Okay, so this seems similar to SYK, and indeed we can solve it in a similar way. What we'll do is, just like we solved the Schwinger-Dyson equations in the low energy limit for the SYK model, we neglect the bare terms. Here they would be this /k and the mass term and bare propagation of the boson. If it has bare propagation, it actually doesn't matter because, as we'll see, it's irrelevant at the critical point. So whether this boson is just a Hubbard-Stratonovich field or it has its own dynamics doesn't really matter so much. So we'll neglect that. Once we neglect it, the equations become scale invariant, and we can, or motivated, and now we're motivated to write power law ansatz for all these Green's functions and self-energies. These are these ansatz. And now it's kind of standard. We plug these ansatz back into the Schwinger-Dyson equations, and then we get a relation. So then the only parameter that will determine the scaling dimension delta, which is an unknown here still, will be the rank gamma. So as a function of gamma, we'll get, we have analytic expressions for it, but you can just plot them. And you see for each dimension, there is a relation between the rank and the scaling dimension of the fermion. So for example, just as an, you can look at the 0 plus 1 dimensional case, and you see that when you take the rank to infinity, infinite rank corresponds to SYK model, because the SYK model is when the matrix is full rank. Here it would be rank n squared. So when you take gamma to infinity, you get exactly, this goes towards scaling dimension 1/4, which is exactly the SYK scaling dimension. If you go to gamma equals 0, basically means that you have just a single boson. The single boson will condense it, and you'll get so they're right. So there are two situations here. You can either go to, there are two types of non-interacting fermion limits. There is a non-interacting fermion limit where the Green's function becomes just the bare Green's function, in which case delta equals 0, and there is a case where you have an effective SYK2 interaction when the boson condenses, and you have an SYK2 interaction that gives you a scaling dimension delta equals 1/2. So these are two limiting cases. In the case of 1 plus 1 dimensional system, you get the free fermion scaling dimension, which is 1/2 for 1 plus 1 dimension. For gamma goes to infinity, for infinite rank actually, and you get delta equals 1, which is equivalent to gapped bosons, gapped fermions, when gamma equals 1/4, which is kind of interesting that this critical solution fails at below gamma equals 1/4. And the reason is, I told you that we need to check a posteriori if the solutions we assumed for example, for the self-energy, for either the boson or fermion self-energy, are indeed leading compared to the bare terms, and meaning that the bare terms are irrelevant. So that actually, in order for this to happen, we need to have this inequality, and in 1 plus 1 dimension, this inequality means that gamma must be larger than 1/4. So it's kind of an open question what state will occur here for if the rank is below 1/4. And what we think, it will still be delta equals 1, but with logarithmic corrections. So, but I'm not so sure. So this is an open question that can be discussed. Anyway, these are the critical solutions. This is just at the basis of one particle Green's functions. Before going to, how much time do I have actually?
2 minutes.
10 minutes?
2.
2 minutes. Oh, whoa. Okay, that went too fast. Okay, so I'll jump on self-tuned criticality here. I just wanted to note that in 1 plus 1 dimension, it turns out that this critical point is stable, is completely stable, meaning that we don't have to tune it ourselves by tuning the mass of the boson or the coupling. It will actually self-tune to criticality. You can show it's an attractive fixed point. In 2 plus 1 dimension, you have a different situation where the critical point is like a normal phase transition. You need to tune it, and you get a phase transition at the critical coupling. And maybe for at least for this audience, maybe the most important thing, what about fast scrambling? So this is the out-of-time order correlation function. It's computed on a double Keldysh contour. regularized in the way that's kind of convenient in this field with Whitman, basically that these two Keldysh contours are displaced by beta over 2. And Kitaev proposed a method to solve this 4-point function in a ladder expansion. So basically, solving this ladder expansion is equivalent to solving eigenvalue problem, where the propagator we're looking for is the eigenvector of this kernel that adds a rung to the ladder. And we're looking for solutions that have exponential growth in time, and here also some momentum in space. This is outlined very nicely, this method, by a recent paper by Gu and Kitaev. And going through so I don't have too much time to go through how this is done, but the interesting point is that when you go through it, there are actually two contributions to the AUTOC. One contribution coming from a saddle point evaluation of this integral, and another from pole. And one the pole contribution gives you fast scrambling when it dominates, but it dominates only in part of the light cone, sufficiently close to the light cone. So what we get is maximal scrambling here, close to the light cone. But for example, at equal X correlation, so autocorrelation, out of time order correlation functions are not maximally scrambling. So we get maximal scrambling only here. And here is a diagram showing what is the scrambling at X equal to 0. So in the middle of the light cone, you see that lambda over 2 pi t never approaches really 1. It's some finite fraction of 1, non-universal fraction, but sufficiently close to the light cone, it's maximally scrambling. This is different, for example, from a holographic model, well-known holographic model, n equals 4 supersymmetric Yang-Mills, which is a maximal scrambler everywhere in the light cone. So I don't know, maybe you should tell me, maybe it's worth a discussion. In what way does this imply, say, duality to gravity? Does it imply duality to gravity or not, and so on? We did not calculate the case 2 plus 1 dimension, which is somewhat more complicated, but I think it can be done. Okay, so maybe I'll also not comment on relation to large N limit. I want to say that okay, so maybe I will say just one word, that this is a new kind of large N limit. It's nice because at the level of the saddle point, we capture anomalous dimensions that in the normal large N limit, where m equals 1, we only get from 1 over n expansion. So we need to go beyond the saddle point to find these effects. Here we find them in the saddle point. And it seems to be extremely accurate because we use this, for example, to compare with the anomalous exponents found from conformal bootstrap. And already for fairly small n, there is amazing agreement. And this is so much easier. This we basically get analytically in seconds. So it's worth thinking of this as this different large N limit that maybe can be used to understand strongly coupled critical points in quantum materials, for example. And we've started to do that. I'll show in the Outlook. Okay, so to conclude, we proposed a new large N limit for the Gross-Nouveau-Yukawa model. It has Lorentz invariant strong coupling fixed points in 1, 2, and 3 dimensions. It's self-tuned to criticality in 1 and 2 dimensions, and is describing a phase transition in 2 plus 1 dimensions. And it shows fast scrambling near the light cone in 1 plus 1 dimension. The outlook is basically, first of all, we have a question: is it a fast scrambler, at least close to the light cone, also in 2 plus 1 dimensions? Is there a nice effective low energy theory in 1 plus 1 dimension, like for example, a chiral Schwarzian theory or a doubled chiral Schwarzian theory. So there is a mistake here. Also, we note that there is some regime of parameters where we find instabilities towards superconductivity, and that can be actually very interesting for applications in condensed matter, where around strong coupling critical points, we also find usually instabilities towards superconductivity. I also want to point out a paper where we actually applied this kind of new large N philosophy, different large N philosophy, to understand a critical point that is very ubiquitous in heavy fermion materials. So that's it for today. Thank you.
Thank you, Ehud. We are kind of out of time, so a few very quick questions. We can also discuss in the discussion session. Okay, thank you, Ehud.